All right, let's get into it, guys. We've already had a little bit of an introduction to statistical hydrology when we talked about precipitation frequency analysis. And we talked about two different kinds of data series, time series of data. Who can tell me the two time series, or at least one that we worked with for precipitation data?
Partial duration and
partial duration. And what was that partial duration series exactly? How do we create that series?
you select the storm and a return period, and then you go on NOAA, right, and get the data from there.
Right, so NOAA has a database, basically kind of like a map. Trying to do two things at once, I don't know if that's the best idea. Which is based off of partial duration series or annual maximum series, which is the other data set that we'll talk about, that we talked about. And the partial duration series, remember, is if you have like a rain gauge or a stream gauge, for example, you have a threshold, and any flood that goes above that threshold is part of the series. Everything below it, we don't count. So we'll be looking at annual maximum series here for flood analysis. And now we're going to go to river gauge data for this part of the class. And annual maximum series, of course, is just the biggest flood or biggest rainfall event in a given year. No matter how big or small it is, just the biggest one that happened. So first we'll start talking about defining and calculating fundamental statistical properties. Of hydrologic data. Distributions. So data series, data distributions. Does anyone remember what a probability distribution is? Dylan, I'll call on you.
As time with a certain duration, there's a probability of an event happening over that duration, right?
Yeah, that's definitely a piece of information you can get out of it. We'll look at distributions in a second, but basically it's kind of like the probabilistic representation of the data. So if you have, small discharges, big discharges, how frequent? It's kind of like a frequency distribution. Would you expect to see a discharge in this range versus this range versus this range? So remember PDFs. So we'll introduce probability density functions. That are used in statistical hydrology. And then we will define and derive a Floateration curve. Using a complete data series. So remember, the partial duration series it's just part of a data series. So we'll talk about stream flow data. And if I wanted to make a partial duration series of stream flow data, I'd pick a threshold discharge value for that particular stream, say 50 CFS. And then I'd strip out everything below that. And so I just keep everything above 50 CFS. For flow duration curves, we use all the data. So if we have daily data, we'll use the whole data record, and we'll look at the frequency and magnitude of flows using that. All right, so the big kind of fundamental question of this series of lectures is, what do we want to achieve with hydrologic data using statistics? Do you guys have any thoughts on that? Why do we want to use statistics and data, and what can we use it for in terms of engineering hydrology?
Future designs.
Yeah, we need to know how to design things. We need to know how tall the bridge should be. We need to know how much flow to expect coming down a spillway. We need to know what the peak discharge we expect to have come through a culvert. And with the rainfall, right? Same idea. How much rainfall do we expect to get under a given probability and duration or frequency? So that's the ultimate goal here. And hydrologic data has a lot of use. And I think we can kind of compare and contrast statistics versus models. And I should say let me just change this real quick. Statistical models versus physical models. Or physically, dang it. Can I undo that? Let's see.
Hey, Joel, really, Jake
Yeah.
wrote a comment. I don't know if you saw it.
Okay. Nope. You mind reading it to me? There we go.
Says,
Thanks, Jake. Okay, I'm going to keep Jake right here. Jake, you need to get a headset so we can hear your awesome contributions to class. So Jake said it allows us to predict worse cases than data have shown. So yeah, and that's exactly the point of statistical models. So let me I got an eraser here. So statistical models versus which we'll call numerical models, or physically based. So right now we're talking about statistical models. Up to this point, except for that little bit that we did in hydrologic design, risk analysis, and dealing with precipitation data, we've been working on numerical models. And a numerical model is just simply you take equations that describe the physical world. Either they are based in physics and mechanics, or they're kind of semi-empirical, and meaning it's based on some data and some physics. And you put all this together and you create like a watershed model, like what HEC-HMS is. Although I should say HEC-HMS has a lot of empirical and statistical information in it. You know, the curve numbers and the equations for the curve number, et cetera. Statistical models is just taking data and making predictions using equations based on the data themselves. So this is empirical. And this might be, these numerical models might be semi-empirical, meaning they have some data in there. Some real world data has been used to kind of parameterize these models, or they could be totally, theoretical. That's the kind of crazy St. Benot's equations that we looked at for flood wave routing. Those are totally physically based. an idea of a statistical model. What's a basic statistical model that you guys know about, that we learned about in statistics?
We're talking about like the CDFs and all those.
Yeah, CDF or a PDF. So probability distribution function. Looks like a hydrograph, doesn't it? This is probability density on the y-axis, and this would be our random variable x, which could be, for example, peak flow or something like that. And this is a model, meaning it's an equation, right? It could be the log normal distribution, could be the, we'll talk about some other distributions. And you can fit these models to data. We talked about fitting in statistics. And then you can use this equation then to make predictions. So for example, I can figure out what is the peak discharge below which 99% of observations occur, right? And that's how we get to recurrence intervals and flood frequency analysis. So a statistical model allows us to fit a model, a mathematical equation to data. And then, like Jake said, we can predict even more extreme events that are beyond our data set. When we did the Weibull plotting position and frequency analysis for the rainfall data, we used a data set, and the frequency storm event that we were able to estimate was limited to the number of years we had. We had a 50-year data set. You can predict, I think it's the 1/51 AEP event, right? So what we're going to be talking about is how do you predict, for example, the 1% AEP event if you only have 10 years of data. So essentially what we do is fit a probability distribution function, and you can actually make it look like kind of like a linear regression function. And you end up with recurrence interval rate, I'll just say AEP. And you can end up being able to predict something way out here that's much less frequent than, say, something over here, which is much more frequent, where you have a lot more data. So that's the general gist of what we're trying to do here. I had a bunch of reviews. So last time I taught this class, no one was able to take stats with me. So I did a bunch of time kind of reviewing discrete and continuous functions and random variables. I don't want to belabor that too much because we already got to cover that, but can anyone tell me what a discrete random variable is, or just a random variable in general? I'll call in Christian.
Isn't the random variable just anything you're analyzing, like rainfall at a gauge, or like the time cars that turn on a light or something like that?
Yeah.
Is that a discrete variable, random variable?
Yeah, so you can take any variable that kind of exists within a population, and we'll just kind of draw a big cloud. This is like a population of values. This variable exists in a population. So because we're talking about stream flow data, we could talk about a random variable being daily average stream flow. Now, from what you guys remember from stats is daily average stream flow, do you expect that to be a continuous random variable or a discrete random variable?
Not continuous.
Continuous, because it could be any value. It could be 100 or 10.735 CFS, right? So that's continuous. It can take on any value, and the probability of it taking on a specific value, right, all the way out to however many decimal points, is basically infinitesimally small. but we think about kind of bins, right, of data. So on a given day, what's the average daily stream flow? That's a random variable, right? Or in a given year, what's the annual maximum peak discharge? Now that's different from daily average stream flow. We'll look at an example of that. So you have a year, what's the value, the maximum flood that you can have in a given year? That's another random variable. So rainfall event, you know, the rainfall depth you have in a 24-hour period over a given year, another random variable. How do we describe, I'm gonna kind of move on from discrete variables because we're not gonna be dealing with them in this section. We're just gonna be dealing with continuous data. So continuous data. But could someone really quickly give me an example of a discrete random variable? Die roll from Jake. So, you know, a die can take on how many values? One of 6 values. And so if we roll a die, it can't be in between those values, right? So that's a discrete random variable. The example I had in my notes was, is it a cloudy day or not? How many cloudy days do we have in a given month? Is it 7 cloudy days? Is it 1 cloudy day? Right? You can't have half days necessarily, at least the way we frame that. So some weather variables can be discrete like that. How many wet days do you have? Doesn't rain anymore, so that's kind of a silly thing to talk about. All right, continuous data. It will rain sometime. Just a little bitter about it right now. Let's talk about how we work with continuous data. And so we're going to be seeing a lot of time series where we have, say, a year and then an annual maximum, discharge. And so let's just kind of write down some stuff here. And often we will round our continuous data, right? Because we don't really care if the annual maximum discharge is 1005.2. We don't need that level of precision. We'll still treat it as continuous even though it's an integer. We've rounded it to an integer. So here's our data series. And we've got just over 100 years for some river. We'll say the Colorado River in Grand Junction. And how can we kind of visualize this data? What's one tool that we've used to show the distribution of the data?
We use the scatter plot to show some of that data, or a histogram.
Yeah, so yeah, you could do, so a scatter plot would look like just the time series, right? If we did for X value, we did year, and we could do discharge over here. And then maybe it looks like something like, I don't know, you know, and these are just connecting all the dots that we have for values. So this is what a scatter plot would look like, which is just a time series, right? And it's good to look at time series, and we'll look at some examples of how time series can give us a lot of good information about flow, statistical properties of the flow. And then Christian also said we can do a histogram, and we did a lot of histograms in R. You guys remember? We'll get to, I think I'm going to have you guys use a little bit of R for this homework. I'm going to write the script for you though, so you can just use it. And for a histogram, We could have our value of Q down here, a random variable, and we're going to look at the distribution. Right, we're going to bin it into different values. Usually flow histograms kind of look pretty skewed like this. On the y-axis, we could have frequency, which is just, the number, right, of it within this bin. We could also have relative frequency, which would be number per total. So if n is the total we have in the series, the number per total. So that's a kind of an empirical way. And then we could also plot this as probability density, where the units are, so the number within this bin over the total times delta x. Or is that per? That's per delta x, sorry. It's a little unclear in my notes. I'm going to have to double check that, but I'm pretty sure that those are the units of probability density. And so to kind of back calculate the value here, you multiply it by the width of the bin. So delta x is our bin width right here. And probability density is an important kind of unit thing to think about, because that is what probability density functions are plotted as. And I think I had you guys plot a probability density function that you fit to a data series over that histogram, just to compare the two. And so we'll note that as delta x goes to 0, we get what ends up being, so these bins get smaller and smaller and smaller, right? We can't have delta x be 0 because there's no probability. The probability of having a infinitesimally small precise value in a data series is 0. But as delta x goes to 0, that's where you get your probability density function, which is that smooth continuous function that you might fit to a data series. Okay. Real quick on probability density functions. So if f x of x is our PDF, and it's a function, it's a smooth continuous function that represents the probability distribution of our data. So something like this. That's kind of like a normal distribution, right? So if this function is this, the equation that represents this line, then if we integrate that from -infinity to infinity, who knows what that is? And so we're just taking the area under this curve. What does that always have to equal to?
1.
1. All right. Good job. You said you guys killed it in transportation with the Poisson distribution. I think it was a Poisson. Anyway, the arrival time distribution. So good job. Glad you can retain some stuff. And we'll get to brush those statistics cobwebs as we do some of this stuff together. All right, so I'm gonna just review some of these statistics that we use to describe the distribution of data. And then we'll look at some hydrologic data and we'll talk about making a floateration curve. Oh, didn't like that. So these are called distribution statistics. And the first one we'll talk about is the central tendency. Anyone know what the central tendency, there's a couple ways we can describe the central tendency of a distribution. I guess I'll draw a smooth curve here. So here's a kind of a log normal kind of distribution. And how do I describe the central tendency of this? What word or function do I use? All right, I'll just go ahead and write it out. We got the mean and the median. These are two central tendencies. And central tendency is just what if I take a sample of this of 100. The central tendency is just basically what's the kind of middle values, right? So the mean is one way to describe the central tendency. The median is another. And remember the median. Actually, let's go ahead and just write these out. So for the mean, we'll describe the mean of a population. Remember that was mu, which is also known as the expected value, right? Expected value. So expected value of X, our random variable right here, is mu. And we can estimate the mean from a sample. We never quite know what mu is, and that is X bar, and this is the sample mean. Which is equal to the sum xi over big N. So if we have n values in our sample, we're just dividing each, we're summing up everything. Actually, I should probably just do this a little bit different. Can't even write the mean out. Sum everything up divided by the number of your samples. And we'll call that the median is the value where 50% of observations fall above and below. So it's sticking right in the middle. You sort below. You sort the data and the median will always fall right in between the 50% mark, the midway point. Now the mean and the median for a symmetric distribution are going to be the same, right? Because if you have a symmetric distribution, you've got equal number of observations on either side of the peak. But for skewed distributions, it's a little bit different. And we always, hydrologic data is typically always skewed like this. And so our mean value, is it going to be to the right of the peak or to the left of the peak?
Right.
Right of the peak, okay. So our mean value is going to be somewhere over here because we have a longer tail, a thicker tail, and we have more observations over here. So the mean is going to be kind of out here somewhere. And then our median, well, it might be out here somewhere too, honestly. Well, let's see here. No, sorry, it's not going to be because we have few observations over here, more observations over here. So the median might be somewhere over here. So they're not going to line up. We use medians often for skewed data because they tend to stick closer to the mode, right? The most probable value is our mode. But and they're not as influenced. They're not influenced by really big values or really small values. So we always hear in the news the median home price, because we always have some homes that are worth a lot and some homes maybe that are worth little, but we don't want to have that skewed by just because a $10 million home sold in the city or something like that. All right, so variance is the next descriptor that we'll talk about. And remember that variance tells you how the spread basically of your data. So if this has a variance of a certain amount, this distribution is going to have a different kind of variance. And Val, I'll call on you. Which curve has a higher variance? Which distribution has a higher variance if we're looking at PDFs here?
The green one?
The green one, yes. And the idea here is how many, yeah, what's the spread of your data, right? And so the green one, there's a bigger probability density farther away from the center. So that means we have higher frequency of larger values and a higher frequency of smaller values. So it's going to have a higher variance, more observations away from the mean. When we calculate variance, we denote it as sigma for the population, and we denote it as S for a sample. Sorry, this is sigma squared and S squared. That's variance. So variance is going to be equal to, for a sample, is going to be equal to the sum of our observations minus some, sorry, this is just for the population, minus the mean value of the population all over n. And this is also known as sigma squared. So this is our individual observation. Here's our mean value, and here's the total number of observations. And if we want to calculate what's called an unbiased estimator of the variance of a sample, then we use a little bit of a different equation. And all we do is we simply we divide by n minus 1. And we do the same thing. We sum up the differences between, in this case, x bar and our individual observations. And that's going to be equal to S squared. So when we have a sample, this is the equation we want to use with that n minus 1 on the bottom. We also learned about, in statistics, the coefficient of variation. Or CEV. And this is simply the standard deviation over the mean, or the sample standard deviation over the sample mean. And it's a normalized thing, and we can use this to compare the variance of different populations. And so, for example, if I want to look at the standard deviation of the Colorado River versus the Mississippi River, the Mississippi River has just bigger values, right? And if I take the standard deviation, the units of the standard deviation is equal to the units of the data. And so it's going to be scaled to the size of the data. So the Mississippi River, the average is, discharge is probably going to be tens of thousands of CFS, right? And on the Colorado River, the average is like around 1,000. So you can't compare the standard deviation between those two. But if you divide them by their mean, then you can, because this is really just the percentage, the standard deviation as a percentage of the mean, normalized by the mean. So I can compare two coefficients of variations, and that'll tell you how variable things are. And so, say for example, the CV of, I'll pick a creek on the Front Range. Let's say, yeah, we're going to talk about Plum Creek, East Plum Creek in a second. It goes through Castle Rock, south of Denver. So the CV of East Plum Creek, say that is equal to 2.5. So the standard deviation's 2.5 times the mean. And then we'll look at the CV of Canna Creek, which is a snowmelt creek that comes off of the mesa. Say that's like 1.1 or something like that. So all of a sudden I can compare these directly and say, well, the East Plum Creek has a much more variable flow. All right, the last one we'll talk about is skewness. And we typically denote skewness as alpha from the theoretical statistical standpoint. And let's just look at what skewness looks like. You can tell me what the skewness coefficient, or sorry, the skewness is for this distribution that is symmetrical.
Zero.
Zero. Good job, Christian. Skewness is zero. And all the skewness tells you is it symmetrical or not? So good memory. If we have, so skewness is zero, I'll just write that here, alpha is equal to zero. If we have something that is skewed like this, we have, I'm just going to double check this because I always mess this up. Pretty sure this is positive skew, but that's what I wrote in my notes, but I'm just going to double check before I tell you. There we go, positive skew. Okay. All right, so alpha is greater than zero. And if we have a distribution that's kind of like this, then we have alpha is less than zero. So this is our positive skew, or skewness. And this is our negative skewness. And to calculate skewness, this is the third moment. So the variance is the second moment. And if you remember, you can kind of compare these descriptors, these statistical descriptors of probability density functions to calculating different moments to a shape. And in this case, it's the third moment. And the way we calculate alpha, 1 over n, sum of xi minus mu to the third, I equals 1 to n. So it's like the variance, except we do this one more time. However, if we want an unbiased estimator based on a sample, and we don't know mu, for example, then so A would be our sample skewness. And alpha is our population skewness. Then we have a little bit of a more complex equation that's going to be n over n minus 1, n minus 2. So kind of like what we did with the variance where we divided by n minus 1, this time we're dividing by n minus 2. There's actually a bunch of different representations of skewness as a sample. This is a basic one. And we can also have a coefficient of skewness, just like the coefficient of variation. And that is alpha over sigma cubed, or A over S cubed. And that allows us to compare skewness across populations because skewness is scaled to the data itself.
Is that an A, Joel?
Yes, A right here, and this is alpha. So I've been using Greek letters for the population statistics, and then Latin letters for the sample statistics. All right, let's look at some data. So let me see if I got this pulled up here. Oh, let me share screen. There we go. So I've gone to East Plum Creek, and this is, let's just take a look. Let me duplicate this. USGS gauge data. Some of you did USGS gauge data for that water data assignment. This is the USGS website. They maintain all the national stream gauges and usually have partnerships. So you can see this is East Plum Creek. Let's take a look at where it is. Location map. So here's Castle Rock, south of Denver, and East Plum Creek. Kind of drains in the foothills. And here's where that gauge is. And it's just downstream of wastewater treatment plant, and that's who helps pay for the gauge. And there it is right there. It's a beaut. Okay. I'm assuming, yeah, they got something in the water that's measuring the elevation of the water, and they have something that's looking down, which is measuring, I think it's like an echo sounder, and it should be measuring the elevation of the water surface. So you've got the water depth being measured here and the elevation of the water surface measured here. Those are redundant measurements, I'm assuming. So if this gets wiped out in a flood, hopefully this one won't. What I've done is pulled up a record of 15-minute data. That's the kind of finest time scale that these data are presented. And here is a flood that happened this past June. I'm trying to think if I remember what happened in June. I don't remember anything special. If anyone was over there, maybe this was a decent sized rain event. So you can see it got up to about 600 CFS. This is a logarithmic scale. So it kind of compresses everything. And that's what it shows at that 15-minute data. And all I did is I went and clicked on discharge, gave it the dates, and it gave me that. Then I went to, this is available data for this site. I went to daily data, which is right here. And I created a plot of the daily data. And this is the average daily data. And you'll note that this is the same time period. The maximum discharge that we saw only goes to 70 CFS, 70 versus 600. What's going on there? Those are the two graphs, 600 CFS, 70 CFS, June 27th, something around there. Can anyone take a guess? Why are those numbers different? Well, let's look at this a little bit differently. So I started an R markdown sheet. And if you took stats with me, you're familiar with this. I'll just kind of walk you real quick through the steps, how I got the data in there. I think you may have done this already before. But I picked the time series that I wanted. I put the dates in here, and it's that different date format. So I started at June 1st. I went to July 31st. Then I clicked on tabs separated. And then I went to go. And it takes a minute to load. And it just spits out these data. It's in tab separated form. If I want to get this into Excel or R, I do Control A, Control C. That selects all the data. There's a lot of entries there. There's like 5,000 entries. I create a text file. And I just paste it in there. And I'll just call that East Plum Creek, 15-minute. So now I have a text file. And then I can bring that into Excel. Do a new blank. I'm going to open, browse to that data. Click on that 15-minute data. And it brings up this import wizard. All I need to know is that it's delimited. So that's checked. That's good. Delimited just means there's something in between the columns. There's something that tells you how to break apart one column from the next. A delimiter. And what's the delimiter? Sorry, delimiter. What's the delimiter? In this case, it's a tab. A tab is just a thing on your keyboard. It's just tab. It's like a space, except more. We know about comma separated ones, right? So that's the default. I can just finish. And what it's done is actually, I'm going to do one more step here. So hang on, guys. One more step. So delimited, tab delimited. Now what I can do is it'll tell you what, or you can tell it what format you want the data to be in. So right here is the date and time. And Excel loves messing with dates and times, as you guys no doubt know. So if it sees that, it's going to take it and turn it into some different format. I don't want it to. I'm going to just say, treat that as text. Don't mess with it, please. Okay, that's the only one I care about. Finish. Okay, so it keeps the original format that USGS gives it. It doesn't do anything funky. So now I've got the data in Excel, so I could use this. I could plot it. If you want to plot in Excel, then you actually do need it to know that this is a date. And then these are my discharge values right here. It's got all these codes, and you can, if you've got, for example, temperature or stage or some water quality variable, you could look up these codes, and this is the code right here, 60, and it tells you what your parameter is. And this is 60 discharge cubic feet per second. Okay, thank you. All right, so that's a basic way of importing USGS data. It's tab separated, and you have to save it to a text file first and then import it into Excel. So just wanted to go over that. So I did that. I actually turned it into a CSV file. I like CSVs. And I brought together the 15-minute data and the daily data. And then I imported that data using this function. And then I'm mostly, we'll kind of touch on R a little bit later, R refresher later. I told R what the date format was, so it could read it as a date, and then we plotted it. And so this is what the data look like in this plot. This is an arithmetic axis on the y-axis, meaning it's not logarithmic, right? It's just equal intervals. And so you can see there's like, why do we do logarithmic? Well, you can kind of see the differences more clearly. But here you can see, obviously, there's a huge peak that came through. Here's the daily average data in green. So we're averaging, right? We're averaging. That's why this peak is much lower, because this peak of 600 happened super fast. It passed maybe in 15, 30 minutes, something like that. Now here's it plotted with a logarithmic axis. You kind of see that variability a little bit more. Kind of compresses the data. So when we're dealing with average daily data, that works fine in a system that rises and falls on the order of days rather than minutes or hours. East Plum Creek is a pretty small creek, relatively speaking. And for smaller creeks, they're flashier. Flashy refers to kind of how rapidly a hydrograph comes up and down. And as you can see, this hydrograph came up and down really quickly within the course of a day. So that if you take the average value for the day of discharge, it's much less than that kind of peak instantaneous discharge. When we look at annual maximum series of data, they are going to be based off of this 15-minute data, which kind of gets you at that instantaneous, quote unquote, peak value, which is really, in this case, a 15-minute average, but we can only go so small in our time steps here. All right, the last thing I want to talk about with you guys is how to do a floateration curve. And I'll just go back to the whiteboard here. We're running out of space. All right, so floateration curve is a way that we can represent a complete series of data. Not a partial duration series, not an annual maximum series, but a complete series. And you've actually done this calculation because it uses the same Weibull plotting position formula that we did for our frequency analysis for precipitation. So here we'll have discharge, and this could be average daily, or it could be our 15-minute data, doesn't matter. Any time series that's complete. And basically what you represent then, so on that, so we have Q on the y-axis, and then on the x-axis you have, we can call it percent of time, a flow rate is equaled or exceeded and so over here we'll have 100%, we'll have 0% over here, and then 50% over here. Sometimes these are plotted on logarithmic axes, and sometimes it's plotted on just arithmetic axes. It just changes the way it looks. So just kind of a basic example is this. And so we have very large discharges are equaled or exceeded very small periods of time. And very low discharges are equal or exceeded for a large percentage of time. So that should be pretty intuitive. If I were to do this with 15, so this is, say this is our average, Q average daily. So if we look at our East Plum Creek and we take that average daily flow record, we could plot something like this relatively easily. I'll show you the kind of algorithm for doing it. If I were to take that 15-minute data, it might look something like this. I don't mean to go below the x-axis there, it's just kind of lower, right? Edgar, why do you think that 15-minute data is showing larger discharges at smaller percent times of exceedance and then smaller discharges compared to the average daily?
It's just because we have, like when rain falls, it falls really, like a lot of it falls in a short amount of time. So in 15 minutes, you could get way more rainfall than averaged over a whole day.
Yeah, absolutely. So it's just kind of going back to that East Plum Creek hydrograph where we had the 15-minute data and the average daily data. Here's the 15-minute data, right? It kind of came up and down really quickly. And then that average daily data was something like this, right? Oh, I should have, I got my colors mixed up here. Sorry, guys. So a floateration curve can tell us a lot. We use this often for, this is kind of a river flow. It's something that is continuously flowing. And I think, I'm not sure if we'll have time if we do this in the homework or not, but the idea is you could say, what's the middle 80% of flows that we have here? What's the probability that my flow is going to be below a certain value? How many days in a year, that kind of thing, would my flow in the river go below a certain CFS? So the way to do this is the exact same way that we do this in for the rainfall events when we did the frequency analysis. So you've got your time series, a date. We'll start with our water year 10/1/1975, 10/2/1975, and we'll go all the way down to 9/29/2020. All right, so we want to kind of keep within the water years as much as possible, right? We've got our discharge, so obviously it's going to be average daily discharge. Okay, not a lot of change, kind of low flows. So this is our initial data series. Then we're going to want to sort, right? We're going to sort descending. And we get a rank column. So we have the highest number at the top, right? And the lowest number at the bottom. So for our rank, we'll do 1, 2, all the way down to, I don't know how many days this is, but I'm gonna make a number up, 22,759, 22,760. And then we do our probability of exceedance, which is the Weibull plotting position formula. And that is our rank, which is M over N plus 1. And N is going to be equal to the total number of data we have in the record. And so how do we interpret this? Probability of exceedance is also known as the percent of time the flow rate is equal or exceeded, right? And you can kind of convert from probability to time by multiplying by, for example, if this is a Floateration curve and we want to know how many days in a year, then you multiply the probability by the number of days in a year, or 365. So you just do this formula, and so rank, this number stays the same, rank's changing as you go down, and then you end up with this. So your largest discharge is going to have the smallest probability of exceedance, and this is the probability that that X is greater than or equal to xi. So where x is a random variable, what's the probability that's going to be bigger than some given value of that variable or some instance of that variable? So we can plot flotation curves and then we can kind of interpret them in certain ways. And I will say, for example, the applications that I'm familiar with rivers are like fish passage or reservoir operation. And so you could use a flotation curve to understand the probability that you'll have certain flow rates in a river. And so if I want to build like a, let's go move and get some new screen here. So if I got a river and there's a weir on it for diverting flow, and I'm going to build a fish ramp on it so that we can get fish to swim upstream. And we know that this particular fish can only swim like it has a burst speed, right? This is kind of an example I'm going to run with here. They can swim really fast for a really short distance of, we'll say, 7 feet per second, something like that. So that means it can swim through water that is less than 7 feet per second. It can actually make some headway, right? So I want to design this fish ramp, and maybe it's going to have some sort of cross section that looks like this over that weir. And I could do a hydraulic model like HEC-RAS, or I could do some basic cross section calculations to figure out what the velocity of the flow is going to be as a function of discharge, right? So velocity is going to be some function of the discharge, and we can do open channel hydraulics to figure that out. So if I got this function, velocity is a function of discharge, and then I have a flotation curve that has discharge and it has, let's just say probability of exceedance, then I can figure out what the probability is and also the time window that the fish would be able to swim up over this, this rock ramp fish passage structure over a diversion weir. And say I know that I can do a flotation curve, just say that the fish are migrating upstream during the springtime. So I could do a flotation curve just for springtime. So that could be March to say June, right? So I take all the flow data from March to June and make a flotation curve. And then I know that my fish can only swim when the discharge is in this range. So this will give me then this window, a certain percentage, right? So let's say this is 0.05, and then this is 0.25. So I've got this probability of exceedance window that the fish can actually swim through this weir during the springtime. So that'll give me an idea. In this case, it'd be 20% of the time, right? Sorry, 20% of the time that it's able to swim through that. So that's kind of an application of a flotation curve for you. There's a lot of them, but it's a good kind of tool to use to understand the frequency of flows over a complete series, right? We're using all the data. So you guys will get to do that in class. All right, that is a brief introduction to statistical hydrology and flow records. Thanks for your attention. Should be back in person next week in case someone else gets sick. But assuming no one else does, then we'll be good. And homework due tomorrow. in the evening, and I will be in person in office hours. So you can come by and check me out in the office if you want.
Hey, Joel.
Yeah.
Can I ask you some questions on the homework if you have time?
Yeah, I do have time.
Okay, great.
Does anyone have questions about this before we do homework questions? Okay. Yeah, go for it, Edgar.
I was just looking at the second